Alright, hey everybody. So today we're talking about this word cancel. I hear students use this word cancel all the time, and I feel like maybe the meaning of it is not so well known, and that it means different things at different times. So I'm not the biggest fan of this word cancel, but I think it's worth a discussion. So this word cancel, what does it actually mean, right? So when you're looking at an equation like this one, if you want to solve an equation like this one, I hear people say things like, oh, we want to cancel out this 3 so that the x can be by itself. I understand what the meaning of what you're saying is, but what mathematically happens when you're saying this word cancel? So if it's that you mean when you add 3 to both sides, in this case, cancel means making a 0, because here we have -3, and if you add 3 to it, it makes 0. So in this case, cancel means making 0. Now you have x is equal to 5. X is isolated because this part made 0. Now contrast that with a solving example like this one. Solve 2x is equal to 10. Okay, you want to cancel the 2. Well, what does that mean? In this case, the way you cancel this 2 is by using division. So you're going to divide both sides by 2, and what happens is that this makes a 1. So in example 1, now we have x equals 5. In example 1, cancel means make a 0. And in example 2, cancel means make a 1. This is why I'm not the biggest fan of this word cancel, because it's a bit ambiguous as to mathematically what it is that you mean. And that can make the difference between understanding what you're doing and not understanding what you're doing. So I prefer just to say what it is that you're doing. Are you making 1s or 0s? So let's start looking at some more complicated examples and see how this word cancel kind of plays out in these more complicated examples. So here, this is kind of the difference between like Math 1 and Math 2, I guess. Maybe you'll encounter a rational expression like this one in Math 2, and I'll hear people say, okay, well the y's cancel out. Well, okay, so this happens. How does that happen? And exactly mathematically what is happening here? Mathematically what's happening is that you're making a 1. You have a number divided by itself, and that makes 1. How are you able to do this? Well, let's have a look at this side example where we're multiplying some fractions together, 3 fractions together. 1/2 times 2/3 times 5/4. So the way we multiply fractions is numerator by numerator, denominator by denominator. So when we multiply these fractions together, in the numerator we'll have 10, because 1 times 2 times 5 is 10. And the denominator we'll have 24, because 2 times 3 is 6, and when we multiply that times 4, we'll have 24. So we know what the value of the fraction is going to be. The value of the fraction is going to be 10 over 24. But put that aside for a second, and I want you to focus on the commutative aspect of this multiplication that's going on here. So what I mean is that if you want, when you're multiplying these fractions together, you can rewrite it like this if you want to. 1 times 2 times 5 over 2 times 3 times 4. And what I'm arguing is that this fraction is actually equivalent to this fraction. Say you wanted to rearrange the terms in the numerator or rearrange the terms in the denominator, you could do that because multiplication is commutative. What I mean is that 2 times 3 is 6 and 3 times 2 is 6. Changing the order of the multiplication produces the same results. So here, this fraction is equivalent to, say, 2 times 5 times 1 over 3 times 2 times 4. In the numerator, you're still going to get 10, and the denominator is still going to get 24, right? And if I wanted to, I could take it a step further and say that this is equal to 2 times 5 over 3 times 2 times the entirely separate fraction of 1 over 4. Because when you multiply these things together, you're still going to get 10 in the numerator and 24 in the denominator. And it's this piece that's especially powerful and useful for example 3. So I don't know how it came to be this way, but eventually people stopped doing this step and just kind of became comfortable with the idea that things just cross out or cancel out. But it's really coming from the fact that we're making a 1. This fraction can be rearranged like this. 2x over 3z times y over y. Because of the fact that we reviewed here, that of this commutative property of multiplication, right? I just rearranged this fraction to appear this way. And well, what is y divided by y? It doesn't just cancel out. What that is a number divided by itself. y over y, or y divided by y, is equal to 1. And when you multiply any number by 1, you get the number that you started with. So this is what's happening when you're canceling the y's out. In this case, it's making 1. In that case, it made 0, right? So this is how we get 2x over 3z. Okay, the reason why this is important is when you get to a problem like this one. When you realize that what's happening is you're either making 1s or 0s, that plays out to be important in this example. So what does x squared mean? X squared is a number, or x is a number, and when you square it, or when you raise it to the power 2, that means multiply it by itself. So what we have in the numerator here is x times x. And what we have in the denominator here is x times x times x. Well, what is all this? Or when you get to math 2, I hear people say frequently, okay, well this x and this x, they cancel out, and this x and this x, they cancel out, right? So what's actually happening, you know now, that what's happening is you're dividing a number by itself and you're getting 1 there. The reason why I'm saying that all this is important is because there's the result of all this is not equal to x, it's actually equal to 1 over x. There's something in the numerator here and it's a 1. So how does this look? How could we rearrange this so that you can better see what's going on? Well, this fraction is the same as saying this. X times x over x times x times 1 over x. So this part is this part here, okay? And this part is this part. And they're equivalent to each other. When you multiply x times 1, you get x times x. In the denominator, x times x times x. Here we have x times x times x. So you can see that they're equivalent to each other. The reason why all this is important is what's going to happen with this? Well, this is a number times itself in the numerator, and this is a number times itself in the denominator. So the numerator and the denominator are the same number. And when you divide a number by itself, you get 1, right? So this whole thing inside the red box here is equal to 1. And what you have left is 1 over x. This is the result. This is one of the most frequent student errors that I see in simplifying an expression like this one is just to put x, when really the result is 1 over x. Because when you go canceling things out, a lot of students don't realize that cancel in this case means a 1 is being produced. Okay, finally now, to the point of to one of the main points of the lesson, to cancel or not to cancel. Another frequent student error that I see is, we'll go, oh, there's x and there's x, let's make it a 1, right? Or let's cancel out the x's. Don't the x's cancel out? No, they don't. They don't cancel out, not in this case, because we can't go through this process, right? You can't separate, this process was made possible through the commutative properties of multiplication. In the numerator here, these terms are not connected by multiplication. They are disconnected by subtraction. And down here, they are disconnected by addition. You cannot separate out x over x. We cannot make a 1. So these x's do not cancel out. And I'll leave it for you, I guess, to prove that one. And that's the end of the story for today.